at the audio. All right. So I'm going to present new topics based on material that we've already been working with. And as such, well, let's do this one first. Doesn't matter the order. All right, so we're going to look at 45-degree angles. Thus far, we've only done 30, 60, 90. Touched upon the quadrantals, 0 degrees, 90 degrees, 180, 270, 360, 0, pi over 2, pi, 3 pi over 2, 4 pi over 2, or 2 pi. Okay, so we want to get more ratios in front of us. There's an infinite number of ratios. We've only looked at a couple in order to get the language a trick. So we'll use the 45. I see my hat. Got a nice colic there today. Yeah, hi, good enough. Might look funny, but that's all right. So let's start with a perspective of pictorial. Well, what do we know in the unit circle? We know in the unit circle that the side length of the hypotenuse is 1. And so if we then extrapolate from there, we definitely know from a Pythagorean relationship that that is 1 unit of area. If this is 45 and this is 45, then these lengths are the same, which means the areas they produce have to be the same. So pause the video, figure out what those two areas are, and I'll just keep going. Well, if they're the same, they don't look the same. Come on, let's do a little better job here. That looks better. Then each of these has to be a half, which means that the length, by definition, is the square root of a half, which could have been written as, well, let's make sure people know, square root of 9 over 4 is equal to 3 halves, which means I could have written the square root of 9 over the square root of 4 and also seen 3 halves. So we'll do that here. So this is the same thing as the square root of 1 over the square root of 2, which obviously can be simplified to 1 over root 2 from your previous classes. We can conjugate that, change the tense by multiplying by the number 1. Root 2 over root 2 is 1, so I'm not changing the size of the fraction, but it sure looks different. Square root of 2 over 2, which happens to be less than the square root of 3 over 2, and more than the square root of 1 over 2. All right, so what's the other perspective? Well, the other perspective is basically doing what we just did, but from a symbolical standpoint. So from the symbolical standpoint, x, we're trying to find those sides. We know that this is 1. So this is the symbolic work that went with this picture. Where am I? Oh yeah, x squared, boom, 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 and x squared, boom, 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 equals 1. Well, that's 2x squared equals 1. So x squared equals plus or minus, but I'm going to ignore the plus or minus here. Just because we've got an actual picture in front of us here. So x squared equals 1 over 2, and now we're at x equals the square root of a half. Right back to where we were a minute ago. Okay, square root of a half. And you should want to know that the square root of a half could be written as the square root of 2 over 2. And I encourage you to put that in your calculator and become familiar with it. Actually, it's on your memorization sheet, but you need to connect with it. My just telling you doesn't seem to do it. And I've gone months in classes where I'll ask after midterm, what's the square root of 3 over 2 as a decimal? And over half the class still doesn't know. Okay, you can't do math if you don't have a feeling for size of what you're looking at. All right, so let's take a guess at what the square root of 2 over 2 is with decimal. Square root of 2 over 2. If you square it, you get 2 over 4, which is a half. All right, so what decimal gets you close to a half when you square it? Well, 0.2 times 0.2, 0.2 squared is, no, that's not even getting me close. 0.2 times 0.2, no, that doesn't get me even close. How about 6.6 squared? Oh, that's 0.36. Oh, that's getting closer. How about 0.7 squared? Oh, that's 0.49. Huh. You know, that's pretty close to what I'm looking for. So it's got to be pretty close to 0.7. And in class, I'll be referring to root 2 over 2 as 0.71. It's closer to 0.71 than it is to 0.7, so we're going to go with 0.71. And it won't be hard to reconnect with that because 2.71 is an approximation for E, and that is just coincidental. All right, but at least every time you see this, you can say, oh, ratios of a 45, 45. All right, so that's one discussion. Now we have 45-degree angles in front of us. Second discussion I want to have with you. And let's rewrite our ratios a little bit differently here. So I'm looking at the cosine and the sine functions. And the cosine of 45 degrees we know is now root 2 over 2. Just as a quick review, the sine of 45 is root 2 over 2. And that's 1. And when you square that and add it to the square of that, you get the square of that. And this kind of notation is going to head you towards vectors, not something we're going to work with here. But I'm going to show it to you so that when you hit your physics classes and different things, you know, there's a trigonometric coordinate system with magnitude, and you're going to be using trig in order to sort those types of problems out. And once you get into physics, you start applying math to the real world here. All right. So where was I? Yeah, I thought I'd just give you a sense of the cosine function is really all about the x-axis. Okay, so we're really talking about the x-axis. And in a unit circle, if our radius is 1, then the cosine of 0 is a maximum. That's the maximum width to the right. Now, I'm not going to write it as 1. I'm going to write it as the square root of 4 over 2. And then as we move around the circle to the next triangle, my width just got smaller. And it turns out that 30 degrees gets us root 3 over 2. And as we move around the circle, there's my 45, 45, and that's root 2 over 2. And as we move around the circle, 60 degrees gets a half, root 1 over 2. And then as we're straight up, there is no width. The width disappears when I'm straight up. When I get to the 90-degree mark or the pi over 2 radius lengths, right? So I think we can see that in the first 90 degrees, we started over here at a max of 1. And after 90 degrees, the width got smaller and smaller and smaller until it went to 0. If you know how one quadrant moves in a sinusoid, then you've got a better chance of learning the first period, starting from 0, of the cosine function. What the shape is, what the range is. Goes up to 1, goes down to -1. All right, well, what happens with Pythagoras? If one side gets bigger, then the other side has to get smaller because the square area, well, I guess I could do it here. The square area is constant. So if this is true, and all of a sudden I make this a little bigger, well, that area got a little bigger, then this one's got to get a little smaller. And whether you realize it or not, I've just started to get you talking about related rates because there's a proportionality here that you'll study in calculus. I'm not sure if you'll ever have this discussion or not. Hang on, I got somebody coming in. Yeah. Yes. Do you need me for anything? No. All right, I'm just going to keep going because I'm making a video for the class. Okay. Let's see. So we were then talking about, oh yes, square areas, related rates, calculus. Now we're going to look at the sine function, which is really about the y values. And the y values, the altitude at 0 is 0. The altitude at 30 degrees is a half, which could have been represented as square root of 1 over 2. 45 root 2 over 2, root 3 over 2. So I hope you can see the inverse relationship. If I square these numbers, 0 over 2 squared is 0. 1 squared is 1. If I add them up, it adds up to this constant area. This one got bigger. This one got smaller. Gets bigger, gets smaller. So there's this inverse relationship because of the Pythagorean theorem. Okay, so I wanted to show that. So what happens in the first 90 degrees of the sine function? Altitudes go up. Y values go up. 0. 30 degrees a half. So I'm not drawing a unit circle here, so I'll stop that. But the sine function then, did I erase the cosine, the first 90 degrees? So let's put them together. The first 90 degrees of the cosine function, the first 90 degrees of the sine function. Remember, x is an angle. All right, and this is a command. We could write opposite over hypotenuse. Well, I was doing sine function. Opposite over hypotenuse. But that's what SIN means. Take that ratio based on that angle. We're doing some very friendly ones that you can do without a calculator. Most trait has to be done with a computer or calculator. All right, so next topic. Yeah, let's stay here. All right, so thus far we've been going from angle to ratio. It is now time to go from ratio to angle. In other words, somewhere in your memory banks is the ability to go from here to here. I don't know if I did that the same way. All right. So the language that came our way, our cosine of x and arc sine of x. So these are the calculations we're now going to study. Now, when I look at the cosine of x, I take an angle and it produces a fraction between 1 and -1. Instead of ratio, I'll write fraction. Okay. What's the inverse of angle to fraction? Fraction to angle. So these are actually the fractions generated. Fractions generated, we'll just keep it there. And we're learning the language with numbers like 0, 1/2, √2/2, √3/2, and 1. So that's where we're going to learn the language of this. Okay. Arc cosine. Well, here's a circle. The cosine is all about the x distances. I think I'll put the x-axis over here, the x-axis. Now, these cosine curves give us, can we see this? Yes. Sinusoids. Repetitive fractions from -1 to 1. Repetitive fractions. If I were to plot every single data point, the inverse, switching the x's and the y's, I get graphs that look like that. Now, I'm not a big fan of a lot of the semantics. It just doesn't seem all that important to me, which means I'm probably missing something here. But this is not a function. I'm guessing because, we program a lot of machines and things that we don't want the machine to say, well, wait a minute, there's a lot of possibilities here. I hit these fractions repetitively all around the circle. Which one do you want? Well, it turns out that mathematicians have decided to restrict the cosine curve from 0 to 180. And that does make a bit of a shape, doesn't it? Yeah, what would I call that shape? Kind of an archway. Oh, an arc. Oh, yeah, I think I can kind of guess where the language came from. And so what I'm going to give you is the base of the triangle. The base of the triangle, if it was here, there wouldn't be any width. Now, where would I have to move so that there's no width? Straight up at 90 degrees. What if I went halfway over? What's going to get me that base? I'm starting to work with this enough. I see 60 degrees. So my x's are actually the fractions, and my y's are the angles. And we'll change to radians soon. And then if I went over √2/2, oh yeah, that 60-degree angle just came down a little bit. Now it's 45. So that's practice, nothing really new there. It's just memorization of what the arc cosine looks like. And so the cosine function starts in the first 90, does that. And so we are looking at 0 gets me 1. So the cosine curve, which means the arc cosine, which could have been written, I'm going to get this out of there. I don't want you looking at that. The arc cosine could have also been written as that notation. And I hope we recognize that notation. as an inverse. All right, so 0 gets me 1. So that's, then we got root 3 over 2. Root 3 over 2 is here. That's going to get me a half. So, sorry, folks. I'm 30 degrees gets you a half. I'll stay in degrees. 30 degrees gets a half. And so over here, the inverse of 1 gets me 0, and the inverse of a half gets me 30 degrees. Now, I just blew that, didn't I? I'm thinking sine function here. All right, I don't want to have to do the video over, so excuse me. That interruption there threw me off of where I was. So 30 degrees for the cosine curve measures root 3 over 2. So over here, I would start with root 3 over 2, try to get that drawing in my head. Root 3 over 2, here's 1. Root 3 over 2 is about there. So that gets me, that's a bad drawing. I need the circle. Boy, did I get taken off my game. All right, so there's root 3 over 2. Back to reality here. Okay, so there's your 30 degrees. And that's what we're going to start playing with each and every day for, I don't know, about 4 more months, I think. January, we got February, March, April, 3.5 months of practice. All right. Sine function. All right, so let's look at the sine function. Now, mathematicians had a choice here because the fractions between 1 and -1, here's the sine function. You remember where it starts? Altitudes do what in the first 90? Go up. Okay, so there's the sine function. Here's -1 to 1. Here's 1 to -1. So they got a decision. Do we want to look at this part of the sine curve and do the inverse there, or do we want to look here? And mathematicians, I don't know who decided or historically, but you've got the unit circle. You've got all of the sine ratios, which are 0, 1/2, root 2 over 2, root 3 over 2, root 4 over 2. All right, 0, 1/2, root 2 over 2, root 3 over 2, and 1. And arcsine could have been written as sine -1, the inverse sine. And the inverse of angle to ratio is ratio to angle. And arc. You know, unit circle, when we make an arc, goes from 1 to -1. But hope you know that the angle here is -π/2. So mathematicians decided to look at all the fractions generated and simply say, well, what are the angles that create these? So sine of 1 came from π/2. The sine of, so the arcsine of root 3 over 2 comes from a, can you visualize it? 60-degree angle. I'll go to degrees. Sine of 90 degrees is 1. Therefore, the inverse of 1 is 90 degrees. The sine of 60 is root 3 over 2. Therefore, the inverse of root 3 over 2 is 60. Then we have our 45. And not the greatest drawing. It's not bad. So therefore, you've got your root 2 over 2 came from 45 degrees because the sine of 45 is root 2. So I hope you get the idea. And then we will, correcting my Western Mass accent, and then we will, start to play with that and start to use it. And that's the inverse of the 2 big. It's also the arctan. If we're doing arctan, we're going to draw the same arc. And just to give you one arctan value that seems to show up in calculus a lot because students have trouble with this. And so the basic one is the 45 degree. 45 degree. And so you might see arctan of what number gives us 45 degrees as an answer. Well, tangent is height over width. It's got to be the same. So the arctan of 1 would have given us a 45 degree gets you 1. So the inverse of that 1 gets you 45. All right. So I got rough around the edges there in the middle, but hopefully you picked up something from that. Okie doke. scrimmage tomorrow.